Today's webinar is on water quality and hydronic systems, and this has been a topic I often reflect back on my work in hydronics. It's been a topic that I really haven't paid a lot of attention to in the past, and yet it's a topic that deserves attention. And it just seems, and within the last few years, a number of issues have come up in a wide variety of hydronic systems that are ultimately relating back to the water quality in those systems. So we've put together, as Harald was saying, an issue of hydronics that covers with water quality, and today's presentation is largely in parallel with that. So what we're going to look at, we've separated water quality into two categories: physical water quality and chemical water quality, and I'll get into those in a little more detail in just a minute. We're going to focus primarily on the second one today, chemical water quality, and in particular, now we're looking at water at a molecular level, as opposed to looking at visible dirt particles or visible bubbles in the water. Those would be physical water quality issues. We're going to be looking at molecular level issues, and we'll be talking about compounds in the water. Specifically, these from a chemist standpoint, they would call these compounds salts, and we'll look at what happens with different salts in water. Some salts are going to cause problems if they are left in the water. And of course, one of the common water treatments that is used in millions of residential systems is water softening, and the question will come up, should I use softened water in a hydronic system, or is there a different type of processed water that is better? So we're going to look at both what happens when you soften water and also contrast that with what happens when you demineralize the water. And again, we're going to focus on the latter category as being the preferred category in hydronic systems. So we'll look at the chemistry of demineralizing water. What is it that's actually taking place? What's the input stream look like? What happens as that input stream is processed through the demineralizer, and what does the output stream look like? And then we'll look specifically at hardware. Caleffi recently introduced a product line called Hydrofill, which is a very simple product to work with. It's basically a one-pass treatment that will demineralize water. So we'll look at what it is, how do you connect it up to a system, and how do you use it in the overall context of flushing and chemically cleaning a system. We'd like to look at getting the water quality in a hydronic system into optimal condition. Involves more than just demineralizing. Demineralizing is the premier process, but if you put demineralized water into a dirty system or a system that has perhaps mixed metals in it without proper treatment, you still don't have optimal results. So we're going to talk about the whole process of filling, flushing, chemically cleaning, and demineralizing the water. And we'll consider that a commissioning step. And as Hot Rod was saying, Hydronics 18 is the issue you want to get that came out in January. That will go into a bit more detail than I have time to get into today. So get a copy of that. So let's start off with physical water quality. One of the issues with any hydronic system is getting air out of the water, as well as getting dirt out of the water, and especially today with high-performance circulators with permanent magnet rotors, any type of magnetic particle, iron oxides in particular, it's important to get those out. And here's an example. This is a zoomed-in photo of microbubbles in water, and Caleffi has solutions for dealing with that, the discal air separators as well as the flow-type air vents, and down here the hygroscopic air vents. So there's a wide variety of products out there to deal with deaerating the water in a system. And of course, another problem is dirt. And again, there are solutions available to clean dirt down to about a 5-micron particle size in both residential and commercial systems. And the other problem we talked about was magnetic particles, and these are primarily oxides of iron. Anytime you have a system that has cast iron in it, steel pipe, cast iron boilers, steel buffer tanks, for example, there's the potential to get iron oxides, and this is especially true if you have tubing in the system that doesn't have a good oxygen barrier, or even with an oxygen barrier PEX tubing, if that system is operating at high water temperatures, the effectiveness of that oxygen barrier does decrease. So we're going to have some oxygen ingress into the system. And this photo that you're looking at here in the upper right of the slide shows a iron oxide sludge that has bonded or attracted to a very strong permanent magnet rotor in one of the new high efficiency circulators, and this can actually cause that circulator over time to bind up. And later on in the broadcast we're going to be asking you a poll question: have you seen a situation like this? Again, Caleffi provides solutions to deal with this, a range of magnetic dirt separators as well as some combined air and dirt separators that have magnetic enhancement to them in both residential size products and also in larger commercial. So in summary, physical water quality, we've talked about it in the past on webinars. There's been several issues of hydronics that have dealt with it, and the latest one is Hydronics 15. So if you're interested in a more detailed discussion on air and dirt separation as well as magnetic particle separation, get hold of Hydronics 15 from the Caleffi website. Now we're going to turn our attention to chemical water quality. In particular, we're going to look at scale-forming minerals that can come in with the makeup water. We're going to take a look at electrical conductivity of water. In general, we want very low electrical conductivity in water. We don't want it to be completely zero, because at that point, a device such as a low water cutoff, which actually counts on the water conducting an electrical current, isn't going to work. But we want to keep that conductivity very low. That will tend to suppress galvanic corrosion in the system. And also we want to talk about minimizing the effects of any dissolved oxygen. Again, this is not bubbles. These are molecules of the gases that make up air, well, specifically oxygen, because oxygen mixed with iron is rust. So again, just some photos. The problem here, probably an oxygen-related issue. You can see a very heavy sludge formation inside that cast iron circulator. The middle photograph here shows the upper section. I have another slide that'll show this a little better, but that's the upper section in a heat exchanger, a stainless steel heat exchanger, fire tube type design. And what's happened here is the scales formed up at the top, and with expansion and contraction of that element, that scale breaks off, and it sort of looks like kind of very stale potato chips there. And obviously, you can see that that is going to be an impediment to heat transfer in that boiler. And then again, back to the conductivity issue. This is a bronze component, looks like some type of perhaps a gate valve, and on either side of that component you can see heavily corroded steel or iron piping. This is a case where we have dissimilar metals, let's say a ferrous metal and a non-ferrous metal, and what causes this is not just the fact that these two metals are put together, it's that the water has electrical conductivity. And later on, again, we'll take a look at that in more detail. So let's move on. Here's a little better view of what's going on inside that boiler we just took a look at. Over on the left, you can see a brand new vertical fire tube design. Again, this is an all stainless steel heat exchanger. Certainly a design capable of high performance, but what's happened here is basically we're looking at the outer portion of this shell that goes around the combustion chamber, actually forms the combustion chamber, and the water would be on the outer portion of that shell. And one of the characteristics of some minerals is that they will precipitate out of solution as the temperature of the water containing those minerals increases. And of course, one of the hottest spots in the system is the heat exchanger in the heat source. It literally is the hottest spot in the system. So the ability of these minerals to come out of solution and form scale on these hot surfaces is exaggerated there. And again, this scale will form as a coating, much like think of it, a thick paint type coating. And with the expansion and contraction of that upper portion of that heat exchanger, over time these flakes will break off and settle down, and again you could see that they are going to inhibit water flow through that heat exchanger. Some of that material is inevitably going to get down on the inside of those that heat exchanger and cause fouling. And I'll show you a graph in a minute that has a profound effect on the efficiency and the fuel use of that boiler. Now let's turn to water hardness. Again, we've probably all heard the term hard water versus soft water. Water hardness is really related to, and I've seen different definitions for it, but it essentially comes down to the calcium and magnesium content of that water. These are two minerals that we want to get out of the water. These are the minerals that tend to cause scaling inside the heat exchanger that we just took a look at, as well as in piping in the system, inside of radiators, and so forth. And oftentimes these materials, calcium and magnesium, as well as some other materials, exist as what are called ions in the water. And an ion is a molecule that's been broken apart into positive and negative charges. Okay? And there are different indexes to express the hardness of water. One of the common ones is grains per gallon. And a grain is actually a unit of weight. It's 1/7,000th of 1 pound. It's the same unit that you might refer to if you're talking about absolute humidity of air, how many grains are in that cubic foot of air. Another one that we're going to work with more today is called total dissolved solids. And that's expressed in parts per million. And you can see there's a conversion factor there between grains and parts per million. There's actually several other indexes that can be used, and there are tables of conversion factors back and forth, but TDS is the one we're going to refer to most today. And here's a map of North America, and this is kind of a macroscopic view, but you can see that the Midwest in particular, and up there in central Canada, tends to have a high concentration of hard water. The southwestern U.S. is also an area with notable hard water. New England area, based on this map, doesn't look to be as bad, but again, I want to make sure you understand there can be pockets of hard water even in an area that shows blue on this map. So depending on the source of that water and depending on what the subsurface conditions are, if there's limestone and so forth in the area that the water aquifers pass through, that can cause a local hardness issue. So again, this is kind of a macroscopic view. It does show it's a serious issue, that there's a lot of areas where hydronic systems would potentially be applied that have hard water. Now, I mentioned the term salts, and normally when I hear the term salt, I think of table salt, but what a salt is in a chemical nature is it's an electrically neutral substance. That means it has a net zero charge. It's not an ion, but it can be broken up into ions. Okay, and there are several common salts that can be present in groundwater. Calcium carbonate is probably one of the classic ones known for scaling potential. Calcium phosphate and so forth. Down at the bottom here, you'll see one that's common. This is table salt, sodium chloride. Okay. Now, these salts, as they exist as a molecule, are chemically neutral. They have a net zero charge, but when a salt dissolves in water, it breaks up into ions. And an ion can have either a positive charge or a negative charge. Chemists will call a positively charged ion a cation, and a negatively charged ion an anion. So I have to be careful how I pronounce those. So cations and anions. And here's just kind of a picture or pictorial representation of what's happening. When we take these salt molecules and put them in water and they do dissolve and they break up into ions, you can see these are just, again, this is not exactly what they look like, but it's a pictorial representation. The thing I want you to notice is that there are negative ions and there are positive ions. Some of the positive ions, like the magnesium ion there, has 2 positive charges. The sulfate ion right here, the SO4, 2 negative charges. And this is important because the charges will determine how these ions will recombine. These charges also determine how these ions can be captured in a demineralizing process. Okay. Now, some salts, such as table salt, sodium chloride, become more soluble as the water temperature increases. That means if you had just a pot with cold water and you put salt in it, table salt, and stirred it around, at some point you would find that the water would not take on any more salt. You'd actually see salt starting to accumulate in the pot. But if you raise the temperature of that water, just put that pot on the stove, bring the temperature up, you'd find that its ability to contain more and more salt increases as the water temperature goes up. Now, other salts react just the opposite, and these are the problem salts. The calcium carbonate would be a good example. This becomes less soluble as the water temperature increases. So if we have cold water in a hydronic system, and we have some calcium carbonate dissolved at a molecular level in that water, when we heat that water in a boiler or a heat pump or a solar collector, any type of a heat source, as that water gets hotter, the ability of that water to retain that calcium carbonate as a molecule decreases, and eventually we use the term it precipitates out of solution. It simply cannot stay as a molecule in the water, and it's going to precipitate out, and that leads to scale formation. Okay, and again, some photos. This is a photo of a cutaway. This is a compact heat exchanger, a stainless steel heat exchanger out of a Modcon boiler. It might be a little hard to see it, but if you look very closely at the inner surfaces of where the tubes have been cut, you can see kind of a whitish gray coating, and this is scale deposits. And notice it's on the hottest part of the tube. That would be the tube that is closest to flame in the combustion chamber. And again, these are going to do two things. They're going to inhibit the heat transfer from the flame to the water, and they're also going to add to the flow resistance in the boiler, which over time is going to cause a decrease in flow rate through the boiler. And you may get into some other issues, such as hearing the water actually boil in a boiler that's not supposed to be boiling it. Sometimes that is called kettling. Here's another problem that can develop. Again, we have a combustion chamber over here on the left with some very high temperatures, a steel wall in a boiler heat exchanger, and let's say we've had a build-up of some kind of a scale on the other side. Well, what can happen is there's a thermal resistance caused by that build-up, and that can cause localized hot spots to form, and over time that can actually cause blistering of the steel and perhaps even eventual failure of that steel, because with the buildup there is not as good a heat transfer through that path, and that, as I say, creates that hot spot. Now, here's a graph. This was actually based on some research that was done at the University of Illinois, and it shows the effect of scale thickness down on the horizontal axis here, and this is in inches, and the increase in fuel use based on that scale formation. And you can see this is a serious problem. With even 1/10 of 1 inch of scale formation, we're going to be just under, maybe we're at 18 or 19% increase in fuel use. We get that up to 2/10 of an inch, and we're up perhaps 34% increase. So the point here, the takeaway, is that even a thin layer of scale buildup on the water side of a boiler heat exchanger that inhibits that heat transfer to the point where the stack temperatures go up. You're not getting the proper transfer into the water from the flame, and the consequence is much higher fuel use. So scale formation is definitely something we want to stay away from. So you might be thinking, well, softening, we should soften the water. Well, let's talk briefly. What softening is a process of passing the water through a resin bed. And down at the bottom here, you'll see a photograph. Now, this is a zoomed-in view of what are called resin beads. And these are polymer beads that are constructed, and they're constructed in such a way that when source water passes through them, calcium and magnesium ions are attracted to these beads. Think of these beads as sort of like a vacuum cleaner for calcium and magnesium ions. they pull these ions out of solution, which is good. That's what we want to do. We want to get rid of the calcium and the magnesium. But the downside is they replace those ions with sodium ions. And this graphic here shows it. We'll start up here at the top where we've got just a droplet of water, and again, representation of various salts and ions in the water. When we pass that across a bed of resin beads, the calcium and magnesium are attracted to the resin beads. So you can see this calcium sticks to the resin, as does the magnesium ion, but the process has to remain electrically neutral. So when a magnesium ion is captured by that resin bead, a sodium ion has to be released. Otherwise, we'd have a buildup of charge. So the net effect of this is we are taking out much of the calcium and magnesium ions, but we're replacing them with sodium ions. And sodium ions do have electrical conductivity. They do contribute to the electrical conductivity of the water, as do some of the other materials. There are some dissolved salts that simply will not be captured. Chloride here and hydrocarbonate here. These are not going to be captured by the resin beads. So some of these salts actually get past the resin beads, and even the magnesium and calcium that is absorbed, the net effect is they're releasing sodium. So what you end up with as an end product here is water that has been, I'll say, partially to largely stripped of the magnesium and the calcium, but it is very high in sodium content, and therefore it has high electrical conductivity. And this is not desirable. I mentioned earlier that high electrical conductivity is going to cause a phenomena that's called galvanic corrosion. And for galvanic corrosion, we need two dissimilar metals, and a good example of that in a hydronic application would be steel and copper, or a copper alloy such as a brass or a bronze. But when these two materials are physically in contact with each other, and that would be represented by this junction right here, and we have an electrically conducting water. That's important. If there's no electrical conductivity in the water, you won't get galvanic corrosion. But with the high sodium content that softened water would have, we're actually having an electrical current that is flowing in a loop here. And when we lose electrons, you can see the electron flow here is from the steel to the copper. That loss of electrons is what we call oxidation or rust. So over time, the less noble metal, in this case the steel, gets pitted, and ultimately it corrodes, and it could corrode to the point of failure. Here's another photo that shows a bronze device here, a circuit setter, and you can see there's a steel pipe screwed into each end of that, and you can see some pretty severe corrosion over here on the steel as on the other side, and yet the bronze itself is not corroded. Now, again, there's a table, and you can find tables like this in quite a few references that shows what's called the nobility of metals. Some metals, gold, titanium, so forth, not metals that we commonly use in the hydronic system. These are very noble metals. They're very resistant to galvanic corrosion. And down at the other end, at the bottom of this table, we have metals that are much more likely to be oxidized or corroded by a galvanic cell. And in fact, you may recognize magnesium down here at the bottom. Magnesium anodes are commonly used as what are called sacrificial anodes in electric and gas-fired water heaters. They sacrifice, they are corroded, and they do that so that any exposed steel behind the glass lining of the tank is not going to corrode. So we want to avoid galvanic corrosion, and the way we're going to do that is get the electrical conductivity down. Okay, and that brings us to demineralizing. Now, demineralizing is distinctly different from softening. That's the first point I want to make. But there are some similarities, and one of the similarities is the nature of the process. Again, we're going to pass the source water, the raw water, through a column of resin beads. And this is called an ion exchange process, and it is similar to what happens with softening, but you're going to see there's a different chemistry here. The beads, the resin beads that are in a demineralizing cartridges, are specifically designed to absorb a wide variety of ions and salts, and as they absorb these materials, these undesirable materials, they're going to release either what's called a hydroxide anion, that's an oxygen and a hydrogen with a net 1 negative charge, or a hydrogen cation with a net positive charge. That's the released ion, not sodium, as would be the case with water softening. And here's a graphic. Let me just walk you through this. We'll start with the untreated water at the top, and you can see there's quite a variety here of ions that I'm assuming in this graphic, sulfates, carbonates, chlorides, sodium, magnesium, calcium. And I also want you to notice that there are two different beads. One of these beads has been formulated to attract anions. And those, remember, those are the ones with the negative charges. And then the other bead has been formulated chemically to attract cations. Okay, so we're able to get both positive and negative ions in the water to be attracted to one of these beads. And I'll just start over here on the left. We'll take a sulfate ion that has 2 negative charges. That is going to be captured by this orange-colored bead, and the result of that is 2 hydroxide anions are going to be released. So again, let's look at it from the standpoint of electrical charge. We have 2 negative charges on this ion going in, so 2 negative charges has to be released. The process has to be electrically neutral. Over here we've got a chloride ion being absorbed that has 1 negative charge, so one hydroxide anion has been released. Now over on the other side it's similar but with positive charges. Here's a sodium cation being attracted to this bead, and the result is a hydrogen cation being released. Again, 1 positive charge being captured, 1 positive charge being released. Now, what's distinctly different, again, about this process, notice the end result is an output of either hydroxide anions or hydrogen cations. And you can probably guess what happens when you take an OH negative and combine it with an H positive. You get H2O, which is an electrically neutral, pure water molecule. So the end result is that you've stripped out the undesirable anions and cations, and you've produced in place of it pure water. Okay, quite a difference. Let's keep going. Now this is done, it's a very simple process. It's typically done by flowing the source water, this would be the raw water, into some type of a column that contains these resin beads. And the flow direction really doesn't matter. I'm showing the flow from top to bottom here. It could just as easily be from bottom up. And again, these are very small beads, in most cases less than 1 millimeter in diameter. But what happens over time is as the undesirable ions are attracted to the resin beads, they eventually load the beads up to the point where they are unable to attract any more ions. And there are chemical processes that can reverse that, but they involve some very strong acids, some very strong bases. They're not processes that lend themselves to use in a field situation. So typically with this type of a process for a hydronic system, we're going to send water through this resin bead column, and at some point it will be loaded where the beads are no longer able to produce the proper amount of demineralization, and the answer to that is you switch the beads. So again, here's kind of think of it as kind of a time lapse where we're putting source water in, and over time you can see more and more of these brown circles forming, and these brown circles represent beads that are fully loaded. They're up to capacity in terms of the ions that they can attract. And we'll start to see that because we'll see an increase in the total dissolved solids in the output water. And at that point, it's time to change the resin beads. Okay, now, we don't want to strip everything out of the water. Completely demineralized water is actually going to be aggressive inside a hydronic system. It is the term that's often used, completely demineralized water, is said to be hungry. It can absorb other materials. It can actually absorb some ions from metals in the system, and it can be aggressive towards the system. So We want to get the electrical conductivity down and get the TDS number down, but not to 0. And here's one reason why. When the TDS gets less than about 10 parts per million, most of the currently available low water cutoff devices on the market fail to function. And that's because they function based on electrical conductivity. If you have a perfect insulator between two probes, there can't be an electrical signal passing through there. So a guideline is to demineralize the source water down to in the range of 10 to 30 parts per million. The low end of that range is enough to let a common low water cutoff device operate. The upper end of that range is low enough that the conductivity of the water is not going to support any significant galvanic corrosion. And there's an easy way to do that. There's inexpensive meters on the market that can be used. This is an example of one. This can give you a readout for total dissolved solids. It can give you the pH of the material, and it can also give you the temperature. And this is probably certainly less than $100, probably in a range of $50 or $60. Now, demineralized water can be purchased, and I've looked into this a bit, and it tends to get expensive depending on what quantity you're purchasing, and also what are the logistics for handling demineralized water. So here's an example. Just go online and do some searching. You can actually buy barrels, 55-gallon barrels of deionized water. Again, same concept, stripped out. It's been stripped out of its salts, and you can see that drum is on sale, $360, but you get free shipping, which when you're shipping 55 gallons of water, I guess that's a good deal. If you buy in smaller quantities, you can see the price per gallon goes up, and from what I've found, anywhere from $6.50 to $40 per gallon for purchased demineralized water. And then there's also the logistics. For example, on a large system, if you have 200 or 300 gallons of water to put into a system, how do you get the water on site? How do you handle those barrels of water? And it's not that it can't be done, but it is definitely not simple. This is a simpler approach. This is the product that Caleffi recently introduced. It's called the Hydrofill. There are two sizes. You see the one on the left is approximately twice the size of the one on the right. And it's a fairly simple device. Inside of this column are bags with resin beads, the same resin beads that we just talked about. And the process is basically put the source water in the bottom. It flows up through the resin beads, and it comes out this connection at the top. And there's actually a meter, and you'll see this shortly. There's a meter that tells you the total dissolved solids content of that water as it's coming out through there. This is the top. It's got a nice locking pressure-rated top. So this is a pressurized cylinder. It can take pressurized water. Now, the resin beads are not just loose inside that. They're actually contained in permeable bags. And I believe the large unit contains 4 of these bags, and the small unit contains 2 of these bags. The water will percolate through the bag material, and then it's in contact with the resin beads. And this is done to make it easy to change the resin beads out. It's a matter of just simply unscrewing the top, pulling the resin bead bags out, and putting new beads in. Here's a photo that shows the TDS meter that's been built into the top. This is actually giving you a real-time reading of the total dissolved solids content of the water leaving the upper connection on the hydrofill. Now, we've talked about demineralization. We've shown you the hardware. Let's talk about kind of a complete process: a flush, a wash, a fill, a demineralize, and a stabilize. Okay? So prior to creating the demineralized water in the system, you should be cleaning, internally washing the system. And here's one reason why. This is a photo. I think, Hot Rod, this was a system that you had flushed out, if I remember right. It's a white 5-gallon pail, and you can see the copper particles coming from deburring the pipe. You can also see some dirt in there, and it's likely, depending on how that pipe's been handled and stored, there could be insects in it, there could be sawdust, there could be drywall dust, so forth. So physically, we want to try to flush this out of the system. Okay. Now, other things that can be in the system: cutting oils. If you're threading pipe, you certainly can get cutting oil in there, and oftentimes threaded fittings come. They have a thin film of oil on them as you buy them. You may be working with an existing system, have some existing debris. Here's a cast iron section turned on its side. You can see it's functioned as a pretty good dirt separator in a sense. Look at the amount of material that has been collecting over perhaps decades of service in that boiler. Solder flux is another one. Okay, this is an acid, and you really don't want to have solder flux in a system, especially if that system is going to have antifreeze in it. And then there's one really bad one here that we came across, and we're not exactly sure where that photo came from, but I think it might have come from New York City. So we certainly don't want that thing going through our boiler heat exchanger. So how do we flush a system out? Well, there's several easy ways to do it. A common way to do it is to set up either 3 ball valves or a combined device like this. Is actually a product that Caleffi sells, where we have a ball valve in line with 2 side ports, each with their own ball valve. And the general idea is we're going to close this ball valve during the flush. We're going to force water in. It's going to go through the system. If we have multiple branches in the system, we'd like to flush them one at a time to keep that flow velocity up. And then the returning water is going to come back. It can't pass through this ball valve, so it has to come out here. Another technique that's been used, and you'll see this sometimes in solar thermal systems, is a check valve, a swing check valve between 2 T's. And it's the same basic idea. When we force water in here, we actually create a reverse pressure differential that will backseat the flapper in the check valve, and we get the same kind of flushing procedure. So it can be done with a variety of valve products, but the general idea is to get a high velocity flush going through there. Think about flow velocities in the range of about 5 feet per second to entrain solid particles such as these copper shavings that you see over here. Okay. So after we've flushed the solids out, we want to do an internal wash, and this wash is set up to chemically clean the inside of the system. And again, Caleffi has a flush cart that's available, and there are products on the market. I've just shown a couple of them over here by Romar and by Fernox. These, I call these hydronic detergents. They are designed to dissolve the oils and the fluxes that would be commonly found in these systems. It's a matter of setting up a flushing procedure like this. It's basically a fluid reservoir with a pump. Same type of valve assembly up here. We're going to pump the water with the washing solution in it through the system. It's a good idea to bring the system up to temperature, if at all possible. The washing action of that detergent is going to be improved at higher temperatures. So just like washing your hands with hot water versus cold water, it's a more efficient process to clean the system. And again, the spent water is going to come back into the container, and it needs to be disposed of based on what the chemical manufacturer over here recommends. Most of these products are biodegradable, but always check on a proper procedure to dispose of that wash water. Now, we've cleaned the solids out of it. We've done the internal wash. The next thing we want to do is a good rinse. All right, we want to get that water, especially water that has the hydronic detergent in it, we want to get that out of the system. And depending on the system, you may be able to do that by opening some drain valves and letting gravity drain it out, or you may do a setup like this. This is just a Schrader valve connected to a boiler drain, so we can put some compressed air in there. And the general idea now is flush the system out, get the wash water out of that system as much as possible. And then we're going to do a final fill. Now, there's a couple ways we can do this. On a smaller system, we can actually run the fill water through the hydrofill, and again, this would be going into the bottom connection from some pressurized source of water. The water passes up through the resin column. This is where the demineralization takes place. It goes into the downstream flushing side port valve and actually goes through the system, pushing air ahead of it, comes around. The inline ball valve is closed, so we come out and you can see some air bubbles coming out here. Now, this works in systems where to purge the air, we want a flow velocity of at least 2 feet per second, and there is a limit to how fast the water can go through the hydrofill product and get proper demineralization. There has to be some reaction time with these resin beads. So recommended maximum flow rates on that small hydrofill unit is 6 gallons per minute, and on the larger one, 12 gallons per minute. If these flow rates are sufficient to generate a good purging effect to get the air out of the solution, out of the system, this is the setup. Now, you want to be careful. You don't want to send a lot of demineralized water down the drain because there is a cost to produce that. So we don't want to waste a lot of water. If we can't effectively flush the air out of the system this way, there is an alternative, and here it is. It's basically you fill the system with source water, and then you're going to set this up as I call this a sidearm process, where we're setting up the hydrofill on a valve. It could be the same valves that we would use for, we've used previously for filling the system. We have a partially closed valve here, not a fully closed valve. Now that's going to allow some of that flow to go through here. Okay, so basically we set up the system. We have water in it so we can get flow through the pumps. We've got the air displaced to the point where we can get flow in the system, and now we're going to demineralize that water. So some of the return water is going to come right down into the bottom of the hydrofill, come out through the top, and go back in. Now, if you think this through, you realize that at first, the rate of demineralization is going to change. It's going to kind of taper off as we get more and more repetitions of the flow going through the hydrofill. So it's important that we take a sample outside of it. The TDS meter on the hydrofill is giving you the TDS of the water leaving, but that's not necessarily the TDS of the water in the loop because of the mixing process. So periodically we're going to take a sample into a nice clean glass container, and again we're going to test it with that inexpensive tester, and we're looking for a TDS reading in the range of 10 to 30 parts per million. So this would be appropriate in a larger system where we have to use some other means to actually fill, and again this is all after the internal washing has occurred. We simply have to get water into the system through another means because of the flow rate limitations on the hydrofill. And then finally, get to this slide, you might be wondering, well, what do you do next after you've got the system filled with demineralized water and it's been flushed out? Well, we want to make sure that the water stays demineralized, and any hydronic system over time is going to have some minor water loss occurring. So Caleffi does make a small demineralization system that would be incorporated right into the fill train here, where we have a backflow preventer. We have the pressure reducing valve over here, standard components in a makeup system, and in between those we have a cartridge filter. And this has been set up so that when the cartridge is new, you have this characteristic blue color to it. And again, any makeup water that flows through here, same thing with the resin beads happens. The ions are stripped out and pure water is put back in, but as with the larger unit, there's a limit to how many ions can be bonded to these resin beads. So when you see the color of this internal cartridge turn brown, it's time to just replace the cartridge. And that cartridge is good for about 30 gallons of water. If you have a tight hydronic system, that should be several years of service. Okay. Obviously, if you have a system leaking that amount of water every year, your first means of attack is to fix the leak. And then finally, I just want to mention one final treatment that we suggest you consider is a film forming stabilizer. And the reason for that is that over time, any hydronic system, and again, I'll point out, especially systems that have PEX tubing and operate at elevated temperatures, there's going to be some oxygen diffusion. And it wouldn't necessarily just be in PEX systems. It could be through the packing glands and valves. It could be through flange gaskets and circulators. Over time, there's going to be some oxygen that is going to get into that system. And this is a final protective step. This forms a molecular thick, very, very thin coating on the inside of the system, and it stabilizes the water. So you have a residual ability to absorb that oxygen. So it's a complete procedure, starting from a internal wash through filling the system with a demineralized water, and then finally adding a small amount of a stabilizing chemical. You've really got a complete approach to high quality water in a hydronic system? I would say yes, especially the galvanic action. As long as that water has electrical conductivity and you've got dissimilar metals, the rate of reaction might be slightly less than it would be in a hot water system, but from a chemical standpoint, everything is in place to create that electrical circuit. So I would say definitely on the galvanic corrosion. And the scaling, again, it's going to depend on what's in the water. We talked about especially the magnesium and calcium. As the water heats up, they become less soluble. So the reverse of that would be that chilled water would tend to hold more of the calcium and magnesium in solution. But that being said, I would not go as far as to say that it's not an issue, especially if the system might also, you may have a system that shares a chiller along with a boiler. So even though in the chilled water operating mode, the scale formation may not be as aggressive, it could be in the heating mode. And the other thing I'll go back to, oftentimes if you look at water distribution piping, just metal distribution piping, cold water pipes can be filled with scale. So I would be definitely mindful that scale formation could be an issue, and would still recommend demineralized water in a chilled water cooling system. Well, it should be certainly less. It may not occur to the point, I mean, if you look at the nobility chart, for example, you'll find that copper and brass are very close to each other, brass being a copper alloy. I'm not aware of galvanic corrosion that certainly has gone to the extent of causing any problems when you mix copper and brass, and we do that all the time in hydronic systems. So I guess I would say from a chemistry standpoint, the potential is certainly lower. Basically, the farther apart the metals are on that nobility chart, the more potential you have, the more aggressive the galvanic corrosion could be. But metals that are right next to each other on the chart, probably insignificant in any effect. Yes. Yes, and that's when you buy premixed glycol, you're getting a good base water. So it is important to, especially with propylene glycol, to have a low ion content of the water. So whether the manufacturer does and sells it to you as a premixed solution, or you take care of it in the field, in either case, getting I think the term we've been using is zero-base water, getting that water down to a very low TDS level for use with glycol. Every application should have it.